We continue our study today on matrices by talking about matrix inverses. So matrix inverses, before we get into those, let's talk about what an inverse is in terms of what you already know. With real numbers, a number multiplied by the number 1 is always going to be itself. Now with matrices, we have something similar, the identity matrix. So with matrices, any matrix that's multiplied by the identity matrix is going to be itself. Now the identity matrix is going to be a square matrix that has 1s running along the diagonal and 0s everywhere else. Here's the identity matrix that's a 2 by 2 matrix. And if I were to take some matrix, we'll say matrix A over here, and I were to multiply these two, the resulting product should be the same as A. And you can double check. 2 times 1 is 2, plus negative 1 times 0, 2 plus 0 is 2. And so you can see how the 1's target the specific element within a certain row, and the 0's will zero everything else out. Now, on the other hand, since we already know that any number multiplied by 1 is going to give you itself, well, with real numbers, a number multiplied by its reciprocal will give us 1. So say you have 2, and you were to multiply it by 1/2, which is the reciprocal of 2, it gives you 1. Now with matrices, any matrix multiplied by its inverse gives us the identity matrix. And so here's an example. Here's A, and here's the inverse of A. And if we were to multiply these two together, we end up with the identity matrix. So you can see here, if we were to do 2 times 1.5, that's 3. Negative 1 times 2, that's negative 2. So 3 plus negative 2 is equal to 1. And you'll notice if you continue with that and finish multiplying it out, you'll end up getting the identity matrix. So we can see and we can show that this second matrix given here is in fact the inverse of A. Take a look at example 1. It says verify that the matrices A and B are inverses of each other. So to do this, we're going to show that A times B and B times A will give you the identity matrix. So really this is just a matter of multiplication. Let's do A times B first. So I'm going to put A on the left, B up on top. I'm going to multiply. So 1 times negative 5 plus 3 times 2, that's equal to 1. 1 times 3 plus 3 times negative 1, that's 0. 2 times negative 5 plus 5 times 2, that's 0. And then 2 times 3 is 6, plus 5 times negative 1, that's negative 5. That's going to be equal to positive 1. All right, we'll do the same thing with B times A and see if we get the identity matrix as well. So I'm going to put B on the left here and A up on top this time. And we'll do negative 5 times 1 is negative 5, plus 3 times 2, that's 6, so negative 5 plus 6 is equal to 1. We'll go down to the next entry. We have 2 times 1 plus negative 1 times 2, that's 0. Negative 5 times 3 plus 3 times 5, that's 0. And then 3 times 2 plus 5 times negative 1, that's equal to 1. So that also gives us the identity matrix. So we have verified that these two matrices are in fact inverses of each other because multiplying them both ways gives you the identity matrix. Okay, so how do you actually come up with the inverse? It seems like these are kind of random numbers. So here's how you find the inverse of a 2 by 2 matrix. When you get to larger matrices, finding the what we call multiplicative inverse of that matrix is going to be more complicated. So we're going to start simple and start with a 2 by 2 matrix. So say you have this matrix here, M, and the elements inside it are A, B, C, and D. The inverse of M is going to be equal to this. So first you have a fraction on the outside, 1 over AD minus BC. This AD minus BC that's in the denominator is what we call the determinant. Now inside of the matrix itself, what's happened here is the A and the D terms have swapped places, and the B and the C terms don't swap, but they become the opposite value. Let's take a look at an example. So say you're given this matrix here, 11, -5, 2, -1, and we're trying to find the inverse. So I'm going to first start off by writing out what the inverse is, and then I'm going to put numbers in. So A times D, that's 11 times -1, minus B times C, that's -5 times 2. And then inside the matrix, we have D and A swapping places, so the 11 and -1 swap places. And then the -5 and 2 don't swap, but they become the opposite. So -5 becomes +5, and +2 becomes -2. All right, so now we have -11 minus -10 on the bottom. That's equal to -1. And so 1 divided by -1 is simply equal to -1. And now you're multiplying by a scalar. So now all you have to do is multiply everything inside the matrix by -1. So this becomes +1, -5, +2, -11. Let's do another example. We have this matrix here, 0, -2, -1, -9. So again, I'm going to start off by writing out what the inverse is and then filling it in. So A times D, so 0 times -9 minus B times C, that's -2 times -1. And then in the side of the matrix, we swap the 0 and -9 and make the -2, -1 both positive. All right, so now in the denominator, we have 0 minus 2. That's going to be -2. So this is a -1/2 on the outside. And now I have to multiply this matrix by the scalar -1/2. So multiply everything by -1/2. We have 9/2, -1, -1/2, and 0. And that's the inverse of our matrix B. All right, one last example. So we have this matrix C, 2, -4, 1, -2. We'll do the same thing as before. We'll find the inverse. So A times D, so 2 times -2, minus -4 times 1. And then we swap A and D. So we have -2 and 2 swapped. And then the -4 and +1 become the opposite. So +4, -1. And now we go ahead and simplify. So we have -4 minus -4. And we'll simplify that fraction. This is the same as -4 plus 4. And look what we have here. We have a 0 in the denominator. Now, because we have a 0 in the denominator, this answer is going to be undefined. What this means is that the matrix C does not have an inverse. So we would say C inverse does not exist. Now, why is that the case? Why can't you find the inverse of any matrix? Well, think of it this way. Even with real numbers, let's say you're talking about 0. What number do you multiply 0 by in order to get 1? That's the definition of an inverse, right? Well, 0 does not have a multiplicative inverse because simply, well, if you were to find the inverse, it would be 1 over 0, and that's exactly the same as what we have here. So just like 0 does not have a multiplicative inverse when we're talking about real numbers, matrices don't necessarily have inverses, and it depends on the determinant. When you find that the determinant is equal to 0, then you know that that matrix does not have an inverse.